you guys. Okay, so any questions about 6, 7, 8, 9 that you want me to go over?
Can you go over number 8?
Sure, let's do 8. After 8, then we'll do 10, 11, unless there are other questions. Okay, for number 8, suppose you start an antique car by exerting the force of newtons on its crank for 0.25 seconds. So now that we know the force and the time, we can get the impulse. But they want angular momentum, not linear momentum, so we'll have to use torque instead. What angular momentum is given to the engine if the handle of the crank is 0.3 meters? So now you know your radius, so you can get the torque. So yeah, so all you have to do is just this. Remember, it's kind of like impulse in a way, where your change in angular momentum is going to be your torque times your change in time. Remember, torque is your force times your radius, and our force is 300 newtons, our radius is 0.3. So our torque is going to be 300 times 0.3, which would be 90 Newton times meters. So now here, I have 90 newtons times meters, and times delta t, which of course is 0.25 seconds. And if you work it out, you should get 22.5. And this will be a kilogram times meters squared times seconds. So that's all you do for 8. I could put up something like that on the test, and it'll probably be worth like maybe 4 points or something like that. Nothing too bad. Anything else from 6, 7, or 9 you guys would like to see? No? Okay. So let's talk about 10. I wish there would have been more room at the bottom here, so I'll have to be creative with how I use space. So 3 children are riding on the edge of a merry-go-round that is 100 kilograms, has a 1.6 meter radius, and it's spinning at 20 revolutions per minute, okay? The children have the following masses. If a child who has a mass of 20 kilograms moves to the center of the merry-go-round, what is the new angular velocity in RPMs? So we're going to convert these to, well, actually, maybe we don't need to convert to radians per second. Maybe we can leave it in RPMs because, you know, if you're using the same units all the way through, I don't think it really matters. But it is, actually still won't matter so much. Yeah, let's just keep everything in RPMs. Okay, so, and they're riding on the edge. Okay, so let me think about this one here. So remember, your initial angular momentum will equal your final angular momentum. Remember what angular momentum is. It's your inertia times omega. And inertia obviously is going to change. And you can think of the merry-go-round as a solid disk, I believe. Yeah, so I'm still going to use yeah, so I'm going to use mr squared over 2. But the mass will change because one of the kids moved to the center. So that's not really impacting the rotation anymore. Well, I mean, it is impacting rotation, but it's kind of changing the mass of what we're seeing here. So what you could do is you could say initial will be your inertia, which will be your new m, which is 100 plus 22 plus 28 plus 33 times your radius squared, which is 1.6 squared over 2. That's your inertia times your omega, which is moving at 20 revolutions per minute. final velocity will be the new mass. So the 28 kilogram kid is moving in. So it's 100 plus 22 plus 33 times 1.6 squared over 2 and times the new final omega. Fortunately, something's canceled from each side. And then you want to solve for omega f. So if we do that carefully, we should have the new combined mass, or the initial combined mass was 100 plus 22 plus 28 plus 33. So 183 times 20 over the final mass, 100 plus 22 plus 33, which is 155. So 183 times 20, divided by 155. And I don't get that. So something's a little off here. MR squared over 2. Unless, if we don't look at that, maybe the 100 won't matter. So let me redo this. So that would be then 83 over 55. Let's try that again. 83 times 20 divided by 55. No, that doesn't work either. I'm not % sure what we're doing wrong here for number 10.
Mr. Almashni?
Yeah, go ahead.
Could you just explain why you like canceled out the 1.6 squared?
Well, that's because the kids are on the edge. So that's going to be how far they are from the axis of rotation. So that's why we're using it as your rate, because you're trying to compute the inertia, the inertia of the rotating object, which is the merry-go-round. The merry-go-round does have 100 kilograms itself, and there's the kids on there as well. But what happens is that when the 20 kilogram kid moves to the center, his radius is now 0, right? So he doesn't really. So now you're only look. So it technically should be moving faster because he's not on the edge anymore. One thing I'm just a little bit. Yeah, no, I'm a little bit confused why this is not working out for us, because you could totally calculate the initial momentum, and then you're supposed to conserve it. But the mass changes. Yeah, I'm not sure why I'm not getting.
Wait, Mr. Almashni?
Yeah, go ahead.
I'm still not understanding, because isn't 1.6 squared divided by 2? That's not 1, is it?
No. I canceled 1.6 squared from 1.6 squared over here.
Oh, okay. Sorry.
Yeah, because the radius didn't change. Yeah, not 100% sure why this is not. We're not getting the answer we see there. But unless there's something else. No, because you're just using the mass. That's weird. Yeah, because I'm almost certain that we should have got that answer, but we didn't. Well, let's just move on to the next part, because I really don't know what's going on with 10. And of course, I won't ask you a question like that if I can't figure it out. So let's go for, let's look at 11 here. Calculate angular momentum of the ice skater spinning at 6 revolutions per second, given his moment of inertia. Okay, so remember, angular momentum, easy. It's going to be your inertia times your omega. But you do have to convert that to rads per second, which is really easy. So remember, 1 revolution is 2 pi rads. So that's going to be 12 pi rads per second. So you're going to do I, which of course is 0.4, and times 12 pi. So if I do that, 0.2 times 12 pi, sorry, 0.4 times 12 pi. Yep, I get 15.1. Or we'll be a little more precise, 15.08. And those are the units, kilograms times meters squared per second. Okay, so that's easy. Part B, he reduces his rate of spin, his angular velocity, by extending his arms and increasing his moment of inertia. Find the value of his moment of inertia if his angular velocity decreases to 1.25 revolutions per second. Okay, so in this case, what you could do, you're conserving it, right? Remember, L0 equals LF. So initially, the momentum was 0.4. That was the inertia. And we don't have to convert the units. You could just say 6 revolutions per second equals your new inertia. And remember, the inertia will change because now you don't have your body as a cylinder. You have your 2 arms as like these thin rods that are perpendicular to the main body. And the new velocity is 1.25. So if I work that out, IF will be 2.4 1.25, which will be 1.92. And this would be kilograms times meter squared. And then finally for part C, suppose they say it keeps his arms in, allows friction of the ice to slow him to 3 revolutions per second. What average torque was exerted if this takes 15 seconds? So we do have to calculate the momentum first. So so I'm guessing the moment of inertia will still be the same as before. Or actually, no, we could just use, let me think about this one here. Yeah, so you can use the same inertia, 0.4. Times the new velocity, but you do have to convert that. So 3 revolutions per second. Remember, for 1 revolution, that's 2 pi rads, so you get 6 pi rads per second. So that's what you're going to plug in for your angular velocity. 6 pi. So 0.4 times 6 times pi. So you get 7.54. Remember, the units are kilograms. Then what you need to do is, remember, delta L equals your torque times delta T. And initially the torque was 15.08. So the change, 7.54 minus 15.08 equals your torque. And it takes what, 15 seconds? So it's going to be negative 7.54 times -1 divided by 15. Yeah, you get -0.503. So I think those problems are more reasonable. I don't know what happened in 10, but it's the Newton times meter.
Mr. Almashny,
Yeah, good.
I was trying out to do number 10, and I think I might have.
You figured out what I did wrong?
Yeah. So
Go ahead.
because it's like 1/2. I think it's like 1/2, and then the mass, and then the something like that. But I think the only thing that's halved is the mass of the merry-go-round, and then the other. I guess the children their masses aren't halved.
Ah,
But I don't know.
interesting. Let's think about that one. Huh. Wonder why that is. Did you get 25.3?
Yeah, I got 25.33 repeating.
Huh. Let's think about that one for a sec. Okay, but hopefully with 11 we're cool. Okay, so let me clear that. So using the mr squared over 2. Okay. Yeah, let's think about this one here. So you're doing this then for number 10. You're doing 100 times 1.6 squared over 2 times its velocity. But then what are you doing with the other masses?
With the other, I just take out the 28 because of the kid that went to the middle.
So wait one sec.
No, the only thing that's multiplied by 1/2 is the 100. So it's 1/2 times 100 plus 22 plus 28 plus 33 times 20.
Oh, I got you. Because 1/2. Wonder why that is. So you're doing that. Doesn't make any sense to me though. So taking half. Yeah, I'm not 100% sure why that's happening though, because I want to be able to explain things and say just do it that way. So anyway, let's quickly go back to 4-5 again before we wrap things up. So let me pull this up here. So let's take a look at maybe so I want to do something that was kind of crazy like this one here. The one with the Superman problem. So I know we did 6, 7, 8, 11, 12. I suppose we could probably do 9. That could be kind of a good one. So for number 9, then maybe I'll ask you guys to work on 10, 13, 14, 15 tonight on your own. So suppose you exert a force of 180 newtons tangential to 0.28 meter radius, 75 kilogram grindstone. What torque is exerted? And then what is the angle of acceleration? It's negligible opposing friction. What is the angle of acceleration? Yeah, that one I thought was a little weird. Okay, so remember, torque is going to be your force times your radius. Your radius is 0.28. So if you simply do 180 times 0.28, yeah, so that's all you have to do for number 9, part A. That's pretty straightforward. You're going to look at 9 here. For part A, remember your torque. It's your force times your radius. Force is 180. Radius is 0.28. So you have 50.4 Newton meter for that one. Then for part B, remember we talked about this in one of our formulas here. Tau equals I alpha. And we are assuming it's a solid disk. So our tau is 50.4. Our I, because it's a solid disk, we use mr squared over 2. Your mass of the grindstone is 75 kilograms. And again, the radius is 0.28. Over 2 times alpha. So just be careful of the algebra here. So I multiply 50.4 by 2, divide by 75, and also divide by 0.28 squared. I should get 17.14 rads per second, so I feel good about that one. So you need part A to do part B, obviously. And then part C says, was there an solution if there's opposing frictional force of 20 newtons? So what you probably would want to do there is kind of figure that your tau net's going to be a little different. So .5 centimeters from the axis. So it's 0.015 meters. So what I'm going to do is I'm going to calculate that torque. Torque due to friction, I'll call it tau F, is 20 newtons times 0.015 meters, which is going to be 0.3. Now remember, our original torque was 50.4. So my tau net will be what I applied minus the friction, which is 50.1. Then do 50.1 equals my inertia times alpha. Now the inertia is right over here. We'll just get that out of the way. 75 times 0.28 squared divided by 2. So that inertia is 2.94. If I do 50.1 divided by that, yeah, I do get 17.04. So the key thing is you have to realize that friction is working against you. So that's going to reduce your initial torque. So our torque initial is 50.4. The torque from the friction was 0.3. Subtract it and then get the new acceleration as a result. That's number 9 there. Which I don't know if it'll last something like part C, but I just want to make sure you guys understand that. So yeah, so I would suggest that you guys try 10, 13, 14, 15. at home tonight. I'll put this as like a homework assignment, I guess. Just try it. We'll have a discussion about tomorrow in class. Also, we will do more review on this stuff. I'll try to find some actually, we do have a review set. Actually, I just realized that. It's right over here. I know we did review sets for circuits and waves already, but we do have a review set on rotational motion. Some of these things here, not quite. So these are a little different than I was hoping. Yeah, not sure if it's quite what we want. I may have to produce actually more new materials for you guys. I'll find some good stuff that will help you guys get more practice with rotational motion. But yeah, we're good for today. So again, I'll just suggest you guys work on 10, 13, 14, 15 later tonight, and just make sure you can get those answers. I think that's a reasonable amount of work. If I find anything else that might be worthwhile, I'll post it to Schoology that you guys can try, and then we'll talk about tomorrow. Tomorrow's going to be fully review. We're going to review waves again, review circuits again, review this stuff again, and then we'll even do more review Friday morning. We'll have a test on Friday afternoon. So yeah, that's pretty much it. Okay, so let me stop the recording.